All right. So, does everybody hear me okay? In my last class, some students were reporting that they had some trouble with their audio. I think that it's possible Collaborate may have made an update recently. So, am I coming through all right on your end? Thank you. Appreciate you letting me know. Okay. Well, let's begin with some announcements. Over the weekend, you should spend a bit of time, if you haven't already, finalizing your reservoir sizing calculations. And in class, I demonstrated how you can use Excel, the procedure you should follow to size the reservoir. So all you need to upload by Monday is your spreadsheet showing those calculations. There doesn't need to be an accompanying write-up. In the final submission, there should be a write-up. But in this draft submission, it's just about the sizing calculations. The next thing on your plate after that is homework 11, which is due a week from today, and that I posted on Blackboard this morning. The exams, which you took on Wednesday, it's my goal to spend the weekend grading those. And if I achieve my goal, then we'll go over the solution together on Monday. And otherwise, it'll definitely be done by Wednesday of next week. So I'll post those and we'll talk about the solution. So now we move on to a new phase in the course. We're beginning our discussion of Chapter 13. And that's where we get into hydraulic jumps, which is one of the non-uniform flow situations that is relatively easy to predict compared to gradually varying flow. We'll talk about this distinction between those two different flow types in just a minute. But before we get into this momentum depth discussion, are there any questions related to the announcements? No? All right. Well, let's take stock of where we've been so far when talking about open channel flow. So in the early days of open channel flow, when conditions were steady and uniform, we were able to apply Manning's equation. And this was our model to relate flow amount to the depth and the geometry of the channel and its slope and roughness. It's an empirical method that's used to just kind of describe conditions if there's nothing interrupting the flow. We have a prismatic channel, that the slope is constant, it achieves uniformity because there's no change in the flow over time. So sometimes that applies and other times it doesn't, but that's where we began. More recently, we were talking about what happens when there's some sort of an interruption to steady uniform flow. For instance, if there's an obstruction in the channel, or if the channel becomes wider or narrower, we can use specific energy analysis to predict what's going to be the reaction. And so our method there was to assess whether we had super or subcritical flow upstream, and then downstream, the reaction to the change would be interpreted by, we set up these cubic equations, found the roots, and then we'd know which route to select based on whether conditions had previously at the upstream location been supercritical or subcritical. So that's what we've done so far, is started with steady uniform flow, and then we used this equation, specific energy, to answer the question, what would be the new flow depth after equilibrium is achieved downstream? So there's something interrupting equilibrium, there's non-uniform flow, and specific energy predicts after we get back into balance what's going to be the new flow conditions, meaning how deep would the flow be in the new channel section. Okay, next, here in Chapter 13, we're going to look at a different type of non-uniform flow. And just as an illustration, what this figure is showing is what if we had two different channel slopes coming together. We had a steep section of a channel that matched into a relatively shallow channel section. And in this steep section, it was steep enough that the flow is going supercritical. And so the Froude number is greater than 1. when it's supercritical flow. Another way that we can diagnose whether the flow regime is supercritical is by comparing the known flow depth to what the critical depth should be. And so this dashed line here is just an illustration of the known critical depth. And remember, for a rectangular channel, we can calculate that relatively easily with lowercase q, the flow per unit width squared, divided by g, all of that to the 1/3 power. Okay, so in the momentum depth function, we're answering the same question of what would be the new flow depth downstream after there's some non-uniform behavior. It was uniform, but then because it intercepted a shallow slope where conditions are subcritical, the flow went from super to subcritical, and that transition in between demands an abrupt change in depth. The hydraulic jump is unavoidable when we have that transition from supercritical flow to subcritical flow. So that's just a bit of where we've been and where we're going. Now, we've talked about momentum before. Last semester in fluid mechanics, we talked about momentum mostly from the perspective of closed conduit flow. So flow through pipes, we saw this momentum equation where what we did was we would treat any control volume with water flowing through it as an element, and then we tracked the flow in and the flow out through that control volume. And any fluid that was on the outside, for instance, if there was flow in a pipe that's to the left of the control volume, we would consider the pressure and the area of the fluid on the outside of our control volume as having a force pushing in whatever direction is normal to that surface. And so P1A1 was to the right. It's like an external force. And then F sub x, remember, that we would say is the force required to hold the system steady. So on the left side of the equation is the forces, and on the right side of the equation is the momentum flow. And so what we did was we looked at the difference between the mass flow in and the mass flow out. And so density times volumetric flow is m dot, mass flow rate. And so then mass flow rate times velocity is momentum. And so the difference in momentum between what goes into the control volume and what comes out is going to tell us what force is required to hold the system steady. So that's just a recap of what we've seen before. Now, in open channel flow, there's also momentum, but we don't have pressure in open channel flow. If it's in contact with the atmosphere flowing through a stream, then the water in a canal or a river isn't pressurized at the surface. So things are a little bit different. Here, this depiction is just showing some water that's gradually getting deeper, just to illustrate that it doesn't have to be uniform flow. We can apply momentum even when the depth is changing. And so 1 is an upstream location, 2 is a downstream location. And so the two terms of this momentum equation are, it's a static term and a dynamic term. And so a term having to do with the momentum of the flowing fluid, and the momentum and forces that have to do with the depth of the water. Now h bar here, h bar means the depth to the centroid. So remember, in a rectangular channel, if the depth is y, then h bar would be half of the depth when we were talking about centroids and the depth to the centroid and all that. So here h bar just means half of the flow depth. So we can multiply this momentum expression, each side of the equation, by the unit weight of the fluid, and then that would give us a force. In the same way that momentum flow in a closed conduit could be understood in terms of a force, so can open channel flow. If we do a units analysis and just take a look at multiplying each term by gamma, we're going to get newtons on the left and newtons on the right hand side of the equation. So this momentum equation is what dictates what happens in a hydraulic jump. It's not conservation of energy in a hydraulic jump. We did have conservation of energy in the specific energy analysis. It was an analysis of where is the energy going. And if we had a step, a delta Z, a step up or a step down, then we're just keeping track of some of the energy is going to overcoming the obstacle, or we're getting an increase in energy if we have a step down. But momentum depth function is not an analysis of energy. It's analyzing conservation of momentum, because through a hydraulic jump, energy is not conserved. There's a lot of turbulence, and a lot of energy is dissipated in a hydraulic jump. But we can use momentum to understand what the downstream conditions are going to be like. So as I mentioned before, the two components of the momentum function are the dynamic component and the hydrostatic component. So that having to do with its depth, and that having to do with the velocity or the flow rate per unit area of the section. All right, so I've already showed you this illustration of something that can cause a hydraulic jump. So here, the shaded area is meant to kind of illustrate the idea of like a turbulent surface that is rapidly increasing in height. And we'll look at some videos today of hydraulic jumps. Sometimes hydraulic jumps are called standing waves. And if you've ever gone whitewater rafting, maybe you've seen a hydraulic jump. Like I've done it a couple of times on the both the New River and also the Gauley. And you can see these, it's usually behind a steep drop. There's a standing wave. And so here hydraulic jumps can occur when you have a steep section that then goes to a flat section. And I think that's what's happening, at least in the locations I've seen on the New River, is usually there's a big drop down and then the standing wave forms after that. Here it's showing it can be before it or it can be after it, depending on the relative magnitude of the slopes. So this is one thing that can cause a hydraulic jump. A hydraulic jump can also occur when you have an underflow gate. So here, this is a metal plate, think. If we have a rectangular channel and there's a metal plate that is deeper than the initial flow depth. Why not was the flow depth under steady uniform flow conditions. So this is the normal depth, and we put in some obstruction starting at the top that's preventing the water from flowing at its normal depth. And so what happens is you'll notice it's getting a little bit deeper as it approaches that gate. So here it was the normal depth, but it's not the normal depth the closer you get to the gate, because the water pools a little bit in order to gather energy to flow under the gate. And here at this location, the conditions are supercritical. Even though the slope, this is showing is the slope is a mild slope, as it's called. It's a slope that wouldn't ordinarily cause supercritical conditions. It's a slope that can't support supercritical flow for very long. You can have temporarily supercritical flow because the water that's coming out of this gate is moving fast because of the pressure behind the gate is forcing it out at a high velocity, but then the water's slowing down. You'll notice it's getting a little bit deeper. And eventually, as it slows down, it transitions from supercritical to subcritical flow and has a hydraulic jump along the way. So we need equations that can tell us what this new downstream depth is going to be after a hydraulic jump. And that's what we're going to learn through the momentum analysis, is how to predict when there is a hydraulic jump, what would be the depths associated with the hydraulic jump. So consider this case C, where the slope is steeper than the critical slope. S sub C means the slope required to cause critical flow. So here it's steeper than that, and that means that normally you'd have supercritical flow, but the gate is impinging on the normal flow depth, and so it's going supercritical and it jumps up to subcritical flow because the depth is higher, to cause enough pressure to force the water under the gate. So this is a pretty complex situation, like the rationale for why things are happening where they are. If we're having the jump before the gate, it was all because we had supercritical flow conditions. And finally, we talked about spillways already. How the flow that's coming down the front face of a spillway gathers quite a lot of velocity, and because of that, drop from the top of a dam back down to the river below. It picks up enough velocity that it's moving supercritical and the water has to go through a hydraulic jump. So we're going to watch a video in a moment that talks about this, and it talks about how the water is moving so fast that it can damage the stream. It has a lot of velocity, and there's energy there that could cause scour. And rivers are just made out of rock and gravel and soil, and if you have water that's moving very fast, it can sweep away sediment, and it can kind of dig through the channel and move things downstream that you'd rather have stay in place. It could erode the footing of the dam if we're not careful about that. So dissipating energy after a spillway is an important part of managing hydraulic jumps. Now, RVF means rapidly varying flow, and a hydraulic jump is an example of rapidly varying flow. It's where the depth changes abruptly. Gradually varying flow is when, it's what the name implies, it's when the flow depth is changing gradually. So HJ hydraulic jump is where it's happening quickly, but here it'd be a gradual variation in flow. It's not going through this rapid hydraulic jump, but the flow is gradually getting deeper from the underflow gate back to where it once again achieves the normal depth. And so this is gradually varying flow. There's gradually varying flow after the underflow gate until the hydraulic jump starts, and then it's rapid. Here is gradually varying flow as the water approaches the underflow gate. So this gradually varying flow might be the most complicated thing of all to predict. And that's what we're going to do in the very last week of classes, is look at a couple of numerical techniques that allow us to estimate how does the water depth change when it's going through this gradual variation. All right, look at this figure. Now in red, I'm careful to note this may look like a specific energy diagram, which you've seen before. At first glance it may look like it, but it's not. The specific energy diagram, remember, had on the horizontal axis, it had E. Here, this is graphing the momentum function. It's not graphing specific energy, it's graphing momentum. So you can, for a certain flow rate and channel configuration, you can calculate the momentum function, and for every certain amount of momentum there are two different depths. Just like that there were alternate depths with the same amount of specific energy, the same amount of specific energy is alternate depths. In the case of momentum, it's called conjugate depths or sequent depths. And it just means it's two different depths that have the same amount of momentum. One is a supercritical depth, the other is a subcritical depth. And here, the interpretation of this point that's the furthest to the left, that still is kind of a critical important point. That is the location with critical depth and a minimum amount of momentum. So we'll do a sketch in Excel to differentiate between the momentum function and the energy, specific energy diagram. In fact, we'll do that now. Let's take a look at creating a graph that has on the vertical axis depth, and then on one figure we'll graph the momentum function, on the other figure we will graph specific energy, and we'll talk about how you would use each. So let me just do a quick print screen here so that when I start up Excel I can just paste this example slide into Excel. You can follow along if you like, or you can just watch, and that's also completely fine as well. All right. So what I'm going to have in here is the flow rate. I'm going to have a column with the width of the rectangular channel, the flow depth that's associated with whatever row we're on, h bar, the cross-sectional area of the channel, the velocity of flow, the specific energy, and the momentum function, which has units of meters to the cubed. Not to the 33. Meters cubed. All right, let me zoom in a bit so that that's not so tiny as you see it. All right, so in this problem it's saying that we have a flow of 15 cubic meters per second. So I'm just going to have, since I want a nice smooth curve, I'm going to have maybe 20 different rows. So 15 cubic meters per second. And we can have, the channel is always a constant 6.5 meters for each of these. But there's a variety of different depth possibilities. You know, if the channel is steep, then you might have a shallow depth. It might be that we have a flow, oh, not 0.02, 0.2. You know, it could be 0.2 if it's a really steep channel. It could be 0.3 or 0.4. Let me do a variety of depths. Oops, 0.8, 1, 1.2, 1.4. I guess I'll just do it in increments of 0.2 through the entire series. And h bar, okay, it's a rectangular channel. H bar is depth to the centroid. So it's half of the flow depth. If we want to go down to the middle, then it's simply going to be the given depth divided by 2. And hopefully you remember that from static analysis of stationary fluids. Okay, the area is simply going to be B times Y. Now, if we know the flow rate, Q, we know the area, then V is Q divided by A. So Q divided by the cross-sectional area. And let me, just for the sake of visual appeal, reduce the number of significant figures because I don't necessarily need to see them all. And I'll drag that down through the bottom. So we may have shallow water that's moving at a fast velocity. We may have deep water that's moving at a slow velocity. Okay, so this isn't actually the same 0.6. If I expand it, just to re-emphasize this point, you know, the precision is still there, even if it isn't being displayed at any given moment. Okay, so specific energy, it's the depth and velocity head. Okay, so it is the depth, here's y, plus v squared divided by 2g. Okay, so I've got the specific energy for this first one, and I can grab onto the side and drag it down through all of them. Now, minimum specific energy is associated with critical depth. So where's the minimum point here? It looks like our lowest value is around 0.8, although I don't know that it's exactly 0.8 because, you know, what if it's 0.81 or 0.79? So I'll use solver in a moment to minimize the specific energy and find what is our critical depth. But before, let's also calculate the momentum function, m. All right, so that is q squared. So q squared divided by g, 9.81, times the cross-sectional area of the channel. Okay, so that's the first term of the momentum equation. And now I'm adding a times delta, h bar. Okay. So we have the momentum function for this relatively shallow depth and dragging the cell down. If I just double click, I don't have to necessarily drag it. If I just double click, it'll apply the formula down as long as there's that many rows. And again, the minima point is associated with the critical depth. So first things first, let me just find what is the critical depth with a solver expression here. In the ribbon across the top, I'll go to the Data tab and activate the solver, because what I want to do, I'll use this row 6 where it's already close to the lowest. Okay, I want to minimize. Okay, so my objective is I want to minimize this value, the momentum function. I could have also done specific energy, because the minimum of either is going to give me the critical depth. Okay, so minimize the momentum function for this row, and I'm telling it can change the depth. Okay, I click solve, and it's going to try a lot of different values, and over here it tells me that it has converged. 0.816 effectively is the critical depth, and that's correct. Let me click OK to keep the solution. Okay, so this minimum E and M is associated with critical depth. All right, so far so good, except for, what's this even asking? To make the momentum diagram and the specific energy diagram. Well, yeah, we're nearly there. We've got the data for it anyway. So let's create a graph that has on the horizontal axis specific energy, and on the vertical axis the depth. So I'm going to insert a chart, and I'll let it be one of these where it's connecting the dots, not even showing the dots. It's a smooth scatter plot. All right, so let me select the data that goes in to that smooth scatter plot. Select data, add a series, and the x values are going to be energy for this one, and the y values are going to be the flow depth for that one. And that's the specific energy diagram that we know and love, where it kind of turns into a flat 45-degree angle line at the top. So that's good. Now let me just add a little bit of flourishes here. Let's turn on a chart title is on. Let's also turn on axis titles so that we can call this horizontal axis title energy, which has units of meters, and then the vertical axis title is simply going to be the depth. And then the title of this is it's a specific energy diagram. And how do we use a specific energy diagram? Well, we use it for finding out what is the alternate depths. I'm going to delete these lines because they don't add a lot in this particular case. All right, and I've got that how I like it, and I'm just going to copy it and then make some adjustments to what is the input data for the momentum depth diagram. So Control C to copy, and I'll paste it, Control V in a different location, and then let's just make some adjustments here. We'll call this one, instead of specific energy diagram, I'm going to rename that momentum depth diagram. And then the data that it's looking at right now, look at the figure is based on depth for the vertical axis, and for the horizontal axis it's referring to the specific energy. So all I need to do is just click and drag over to the momentum column, and it's going to give me a new figure based on that column H. And so the shape is a little bit different. Let me zoom out so you can see the shape of the momentum depth diagram. And I may need to change the extents of the figure. You know how it's kind of like going all the way out here to 50? Oh, it may be a more meaningful figure if I instead format the axis so it's only showing through a maximum of 20. And there we have our momentum depth diagram. So there's the critical depth, and I might even want to change the vertical axis here too, so it only goes through maybe 2, zooms in on the data that I'm interested in seeing. All right. So there we have seen the contrast between a specific energy diagram which becomes linear and a momentum depth diagram which does not. Both of them have minima points which correspond to the critical depth. The momentum depth diagram is used for hydraulic jumps. So there's going to be one depth that is a subcritical depth upstream of a hydraulic jump, and another depth downstream which is upstream is supercritical and it transitions to subcritical downstream. All right, well, let's watch a little video that I found that's pretty interesting about hydraulic jumps. I've never been 100% sure whether my system audio comes through to you though. So if you can't hear well, please let me know. All right, so as that video just showed, this is a cross-sectional view of a hydraulic jump. And so there's an upstream depth that is supercritical, a downstream depth that is subcritical, and through that transition, momentum is conserved. Energy is not. And that's oftentimes the whole point of forcing a hydraulic jump, is to dissipate the energy. Now, to calculate what the new downstream depth is going to be, it's often valuable to be able to calculate the magnitude of the Froude number upstream. So we want to know, in other words, how supercritical is it? Remember, anytime the Froude number is greater than 1, that indicates supercritical conditions. But the more supercritical it is upstream at 1, then the bigger the jump is going to be. If you have it really shallow, very fast-moving water, then it's going to jump up to a very high depth downstream. So finding the magnitude of the Froude number upstream is important, and this function will find it regardless of the shape of the cross section, and this function, remember, is only valid for rectangular channels. So conjugate depths are those depths that have the same amount of momentum but different depths. So we've just calculated the momentum function here, and so there are two different depths that have the same amount of momentum. For instance, if we just look at, this is almost 10, what would it take if we did like 0.38? That's getting closer, 0.37. All right, so 0.37 has a momentum of approximately 10. And then if we have 1.5, that is approximately 10 as well. So you could have two different depths with the same amount of momentum. And the name of those two different depths is that they are conjugate depths. And so you can find the conjugate depths graphically by depicting a momentum depth curve and going through that process of finding out what are the two different depths for the same amount of momentum. So that's the approach that's illustrated here. And by the way, there is a physical significance to this. The y1 and the y2, the difference in the upstream and the downstream depth is how high the hydraulic jump is going. So look at there's y1 and y2. So there's a delta z between them. The change in elevation between upstream and downstream. So the change in elevation is the gap between the two legs of that momentum depth diagram. So sometimes you'll be told how high is the hydraulic jump, and so you can find what are the two depths that go with it by looking for at what point are these two curves a certain distance apart. So if you're, it's saying here the y1 is 0.6, And so here's the 0.6. It has a certain amount of momentum. The other depth is going to be between, so the 0.6 had 5.33. So the conjugate depth is going to be between 1.2 and 1.5. So you could just play around with one of those numbers until you found the goal momentum function that you're looking for from the known upstream depth. The other way of doing it, besides iteration or graphical techniques, is this Bellinger momentum equation. So this equation is saying what is the downstream depth, so that's after the jump. 1 is always upstream, 2 is always downstream. So the depth after the jump is the upstream depth divided by 2, and then what's inside of this momentum equation takes into account a measure of how supercritical the conditions were at 1. And so one way of doing it is with the Froude number, as you can see. So the Froude number characterizes how supercritical it is upstream. Or the other is by the ratio of depths. Remember that sometimes we diagnose flow regime by looking at the Froude number, meaning is it greater than 1? But we can also diagnose flow regime upstream by comparing the flow depth to the critical depth. And so this is just another way of conceiving of whether conditions upstream are really supercritical. But note, whereas the Froude number is squared, this ratio of depths is to the 3rd power. So don't make the mistake of squaring it. So this is called the Bellinger momentum equation. And it has some assumptions that we have to be aware of before we apply it. It's assuming that the velocity distribution is uniform. And this is a tricky one. It makes the math a lot simpler. But do you remember what I mean by velocity distribution? Let's look at a channel profile. Velocity distribution is saying, you know, what's the speed of the water at the bottom versus the speed of the water at the top? You and I know that the reality is the water at the bottom of the channel isn't moving as fast as the water at the top. The water at the bottom is experiencing the shear stress that's applied by the unmoving surface at the bottom. And so there's a low velocity at the bottom and a high velocity at the top. There's, in other words, a profile. Well, that would be really complicated to calculate the effect of that profile. So the Bellinger momentum equation says, well, let's just assume that it's a constant velocity profile. It still does okay in predicting downstream depths, but that's the assumption that's probably the furthest from reality, is this assumption about uniform velocity distribution. The other assumptions are maybe a little bit less flagrant, assuming hydrostatic pressure distribution. Now, hydrostatic pressure applies when the water isn't moving. But since the water is open to the surface, as you go down through the water, the pressure does increase in roughly the same rate as it would if the condition was hydrostatic. So this horizontal bed is saying assume that it's a really shallow slope, that the downstream depth is just because of the hydraulic jump and it doesn't have to do with other gradually varying flow effects. And boundary shear stress is negligible is kind of related to the velocity distribution assumption. So those are the weaknesses. Every model has simplifications. Reality is complex. The way that we describe reality is always by necessity simplified. So it's important to keep those assumptions in mind. This equation allows us to quantify the magnitude of energy that's lost when there's a hydraulic jump. Now the units of delta E is going to be meters. And so by now you're accustomed to thinking about energy with units of meters, but this also is going to assess the magnitude of the energy change with units of meters. All right, so it is 1:47. We don't have time to crunch any numbers quite yet. When we get together on Monday, we're going to do some hydraulic jump calculations, and you'll get a chance to try out the Bellinger momentum equation. Between now and Monday, though, you might consider finishing up phase 3 if you haven't already. And then homework 11 is on the web now. It's in Blackboard if you'd like to get a start on that. at least look it over. It's there. All right, well, that's it for today, everybody. Hope you have a nice weekend, and I will see you in class on Monday. Thank you.